Comparison between thermal radiation and light rays. Number 1. Thermal radiation and light rays both are electromagnetic and transverse waves. Number 2. Radiant heat like light rays travel in straight line with the speed of light and both can travel in vacuum. Number 3. Both of them obey laws of reflection and refraction. Number 4. The wavelength of visible light, which is in the range of 400 nanometer to 800 nanometer, or in angstrom it is 4000 angstrom to 7800 angstrom, is smaller than that of thermal radiation. Energy distribution spectrum of black body. This is the energy distribution spectrum. In 1899, Lumar and Pringsheim, from the experimental result, obtained distribution of emissive power E lambda along this direction and wavelength lambda of black body radiation at different temperature. Observations of black body energy distribution spectrum. Number 1. For a particular temperature, the emissive power E lambda of a perfectly black body increases. For a particular temperature, emissive power E lambda is increases with an increase in wavelength. Wavelength is increasing and becomes maximum at this point. Here the wavelength is lambda m, maximum point at a particular wavelength. With the further increase in wavelength, if we increase the wavelength, the emissive power decreases. With the increase in wavelength, the emissive power decreases. Number 2. The maxima of the spectrum shifts from higher wavelength region towards the shorter wavelength region as the temperature increases. That means this is the maxima, this is another maximum, this is another maximum. The temperature is less, more. So maxima of the spectrum shifts from higher wavelength region, this is the higher wavelength region, towards the shorter wavelength region as the temperature increases. Just come back to the previous slide. This is the maxima, then shifting this, then shifting this, then shifting this. Lambda m represents the wavelength of maxima of a spectrum at temperature T. This is the distribution in terms of frequency. Here, if the locus is moving from this direction to this direction, here it is moving from this direction to this direction. So you can write lambda mt is equal to constant, while lambda m represents the wavelength of maxima of a spectrum at temperature T. For this one, so this is the lambda m here, and its corresponding temperature is 200 K. So lambda m into 200 is a constant. Wien's displacement law. As we see from the previous graph, lambda m corresponding the wavelength for maximum emission decreases with temperature. It was Wien who first discovered mathematically that lambda m is directly proportional to the temperature, or lambda m is equal to B by T, where B is called Wien's constant and its value is 2.898 into 10 to the power minus 3 meter Kelvin. The above law is known as Wien's displacement law. This is very important as it helps us to find the temperature of stars or hot bodies. Wien's displacement law may be expressed in terms of frequency as nu m is equal to Ct by B, as frequency is inversely proportional to the wavelength. Wien's distribution law. William Wien also used thermodynamics to show that the spectral energy density between lambda and lambda plus d lambda range is given by E lambda d lambda is equal to A by lambda to the power 5 function of lambda t d lambda. This function of lambda t can be expressed as e to the power minus small a by lambda t, where capital A is equal to 8 pi hc and small a is equal to hc by k. So we can write the equation E lambda d lambda is equal to A lambda to the power minus 5 e to the power minus small a by lambda t d lambda. So already we have discussed A and B are the capital A and small a are the constants. Wien's distribution law only can explain the shorter wavelength region of the black body radiation spectra. If we come to the previous, this is the shorter wavelength. This region is a shorter wavelength. It can explain only the shorter wavelength region. Higher wavelength region, it cannot explain. Rayleigh-Jeans law. Rayleigh-Jeans applied the classical law of equipartition of energy to this electromagnetic black body radiation. They found the energy density of radiation of wavelength lambda and lambda plus d lambda of a black body at temperature T is E lambda is equal to 8 pi kt by lambda to the power 4 d lambda. That means energy density E lambda is inversely proportional to the fourth power of its wavelength lambda. The energy density E lambda is increasing with a decrease in wavelength, as it is inversely proportional with the wavelength. Rayleigh-Jeans considered few assumptions to overcome the failure of Wien's distribution law to explain the experimental result for a longer wavelength region. The assumptions are: number 1, the thermal radiation cavity is full of standing waves of electromagnetic radiations of all wavelengths. The walls of the cavity are perfectly reflecting. Number 2, the number of oscillators means mode of standing waves, per unit volume within the frequency range nu and nu plus d nu is given by n nu d nu is equal to 8 pi nu square by c cube d nu, where c is the velocity of light in vacuum. Number 3, average energy per degree of freedom of an entity can be written from Maxwell's law of equipartition of energy as E average is equal to half kT, where k represents Boltzmann constant, whose value is 1.38 10 to the power minus 23 joule per Kelvin, and T is the absolute temperature of the system which contains the entity. Entity means harmonic oscillator, gas molecules, etc.